we have Professor Arindam Banerjee from IACS Kolkata. He's going to talk to us on self-associating peptides for sustainable development.
Calling me and giving me the opportunity to present what I've about last 2 decades. Just I'll be talking this one, the self-associating peptides for sustainable developments. I belong to the institute that is the most prestigious and the oldest living institute in India. And see, these are the 3 pillars of sustainable development. One is the just for make some healthcare materials, energy materials, and they can find some applications in environmental remediations. So I will be mostly covering these peptide-based biomaterials for drug delivery vehicles at the targeted site. It finds some applications as antimicrobial agents, anti-cancer agents, and making these gel-based materials as a platform to grow through 3D cell cultures and all. If I get time, I'll just talk to this one, that removal of toxic organic dyes, some hazardous metals like lead, cadmium from the wastewater, oil spill recovery, reusability of the, and last but not the least, using metallopeptide gels for water splitting to generate green hydrogens. So I'll just touch upon these things. What is gel? Gel is easier to recognize than to define. Actually, that is the electron micrography picture, the same picture of the gels. If you just look at that, forms a mesh structures, nanomesh structures, and you see there are a lot of interstitial spaces in between, and these are occupied by the solvent. If it is water, it forms hydrogels. If it is hydrocarbons or any organic materials, they form organogels. If it is air, they form aerogels. If it is ionic liquid, they form ionogels. And some of the cases, so it's a viscoelastic, pervasive materials with a lot of space in between, and they are occupied by the solvent molecules. These 2 terms, that the storage modulus and loss of modulus, these are the measure of elastic part and the viscous part of the gels. And for an ideal liquid, G prime is 0, and for an ideal solid, G double prime is 0. But for viscoelastic things, actually, G prime is always greater than G double prime. That shows the dominance of the elastic behavior over the viscous behavior. So now I ask the question, why peptides? Because these peptides is a good functional groups which are just clinging here and there, and they can just self-assemble utilizing all these non-covalent interactions which has been listed here, starting from hydrogen pi-pi interactions, electrostatic interactions, Van der Waals interactions, and hydrophobic interactions to form supramolecular assembly that can entrap and immobilize many water molecules under suitable conditions to form gels. These are all the structural aspects. But if we use these peptides, carbohydrates, or any of the nucleic acids to make hydrogels, they are biodegradable, biocompatible, and they exhibit some of the cases this stimuli responsive behavior. That means if we change this pH, temperature, salt concentrations, or any of the chemicals, that's additives or just removing of additives, even this photo, we can just change from gel to solution and solution to gel, that transformations. Just imagine a situation, it's a messy things, it's having a lot of white spaces. We can just incorporate dye, drug, DNA, RNA, siRNA, mRNA, whatever things you need at the targeted sites to be delivered, and we change this pH slight, then gel to salt transformations occurs, and that will deliver at the targeted sites. So I set out my journey long back, and here that's a tetrapeptides composed of glycine, alanine or phenylalanine, then comes isoleucine and leucine. It just forms that cross beta sheet structures just utilizing hydrogen bonds, mostly pi-pi interactions, and of course electrostatic interactions. This is not the case that CO2 minus and NH3 plus. I'm sorry about this. They solved this type of things. These are the structural things which I got from FTIR CD, and another thing I forgot to mention, that's the small angle neutron scattering and X-ray scattering data. We're having everything. But the thing is, most importantly, they can entrap that doxorubicin, a potent anti-cancer drugs, and have the slow release over a time of more than 48 hours. But there are some shortcomings associated with these things. We cannot use these things as a drug delivery vehicle because this is made inside our body. All enzymes are alpha L amino acids. So how to tackle this problem? One of the easiest way to tackle this problem is to make some non-coded, naturally occurring amino acids to make these peptide-based hydrogels like beta-alanine, GABA, some of the D amino acids which are being present in the natural systems, like alamethicins, zerbamycins. They are having D residues like D-alanine, D-phenylalanine, and D-leucine type of things. So here, actinium-based molecules, they form stable hydrogels at physiological pH and temperatures, injectable gels, slow and sustained release of the anti-cancer drug doxorubicin, but proteologically unstable. They showed very good non-cytotoxicity. Now, the thing is, being a chemist, I can think, can I change the structure a little bit? Say for hexyl, L-alanine, these two things, if we just substitute the forms in water a certain pH, that cross beta is structured but unable to form. You don't have to make any of the amino acids, difficult amino acids. What you do, you are having a lot of the questions, what can be done? So I'm asking the questions, does this chirality and its positions along the sequence affect the self-assembly, gelations, or any other functional property? Can you tune the gelations and the drug release of the gel-based biomaterials by changing the chirality around a particular asymmetric centers of a gelatin molecules? And by this way, we can say, summarize these things, can we think of a path to design the peptide-based biomaterials with tunable functional properties? See, there are 8 stereoisomers are possible. These are the mirror image of these molecules. All of these things are synthesized, and fortunately or unfortunately, LLL, DLL, LDL, this LLD refuses to form gels. Not only this is similar conditions, but also wide experimental tested conditions from the pH 3.5 to 8.5, and so why is it so? We are having a closer look about the structures from the XOD data and all these things we are getting. That's 4.7 angstrom. That's a typical distance between the two cross beta sheets distance. So they all form cross beta sheets. But here that's a 3.7 angstrom distance. That's the centroid to centroid distance of the two phenylalanine stacked together. So FTIR data you see in these two cases, LLL and DLL, all these things, hydrogen bonding and these things are present, free NA stretching. Here LDL, one is missing, that the NA stretching frequency. Here LLD, that's NA stretching frequency, also this hydrogen bonded, that CO stretching frequency is missing. So they just packed differently in the assembled state, and that's why this refuses well than the other two. Now this is the way they speak, that stack, and you see their morphology are quite similar, but their experimental things are different. But you see there's a comparison of the mechanical strength. This mechanical strength was, there's a mechanical strength very good for LLL, DLL, and LDL. It is still lesser. So now this is the proteolytic stability, that DDD and LDD is very stable compared to others. Now the thing is, here you see that drug release property. Drug release properties are different. You see this, what we expected, just flat, that parallel to the x-axis. But one heterochiral residues, this drug release is more. This is because when this drug is just interacting with the jelly things, they are using these non-covalent interactions, is very tight interactions, so it doesn't want to release after some times, but is a less tight interaction, so the release is much more. And that is that drug release of this DDD and LDD, that's a counterpart, that mirror image counterpart. And now we have come up with the magic molecule, that LDD, which shows very good stability, and T-gel is also good, that's 62 degrees centigrades, and doxorubicin release is 76.4%, and proteolytically stable up to 80 hours against proteinase K and chymotrypsin. So, and this assay, that MTT assay, also shows good stability. See, this is the minimum gelation concentrations. We have used much more than that. It's also showing good cell viability assay. And now we all know that we are in an era of this antibiotic resistant molecules. Actually, how to work, most of you know that they just change the permeability of the outer membrane and inner membrane of the gram-positive and the gram-negative bacteria, and they just change these membrane potentials, that's the mode of actions, and they also actually use these productions of that reactive oxygen species, ROS generations, and this is a glossary of different type of peptides which have been making, and these are all published papers. Some of these things are just communicated papers. We are making some plethora of molecules which actually exhibit these antibacterial properties. See, it's not always true that we need these cationic and amphiphilic peptides. Of course, we need these amphiphilic peptides and cationic peptides. In some of the cases, some anionic peptides also good, better results. So this shows this antibacterial properties. I'll just skip off this one also. This is a new molecules which we made. You see, purposefully we have made the C-terminus, that triphenyl phosphoniamine. Triphenyl phosphoniamine is a known one for target, and a just lipophilic tail that will self-assemble to form these micellar structures. They are very good against these ovarian cancer cells, and they can also kill these or dead these gram-positive and gram-negative bacteria. See, these are the evidences here. That's another, these are here, actually, this, not this triphenyl phosphonium things here. We have used this lysine, then histidine, and then leucines, and see look at their activity against triple cancer. This triple negative breast cancer cells, they are active even in micromolar concentrations, and here actually the pathway is caspase 3, caspase 7, this release, and previous this not the case for the previous one. These are not mitochondria dependent pathway, that's a mitochondria independent pathway, some other pathway. For the paucity of time, I'm just skipping off these things here. We have used this peptide gel based things for, and these are the things 2D and 3D cell cultures we did. And here I'll change my gear. I'm just almost come to the last portions. We all know that dye removal is a great problem because these dye are hazardous materials. They decrease the gas solubility in water. They inhibit this growth of aquatic biota, flora and fauna of the systems. So we have used these peptide-based porous materials for removing these things. And here you see these are the gels. This is the dried gels which can absorb and clear these things in an experimental portions. Here they say self shrinking gels. I'll show these things. Actually, within 7 days, they are shrunk to a greater volume. All other things that dyes can be absorbed by using this. And here we have having this capacity also. Now, why this is so, that binds to a hydrophobic dye ANS and increase this fluorescence, so that binds to the hydrophobic pocket and do this action. So I will just come, we have come up with these molecules which shows the 3 different purpose: removing toxic organic dyes, hazardous lead and cadmium from wastewater, and it has been used for oil spill recovery also. And you see within 30 minutes is gellify these things, and 1 gram of the gelatin molecules can be able to gelate around 200 milligrams of this. That has been covered by one of the Bengali Delhi. And recently we got some of the other molecules which can be able to just gellify even the sea waters and all these things. I'm sorry, I cannot disclose because that's a patent. I'm going to patent on these things. And last portion, using these peptides, metallopeptides we have made, they can chelate these things, reduce the sunlight. They form that nanoparticles, decorated nanohybrid things, and that has been used as a nanocatalyst for water splitting. And see, these things as evaluate there's hydrogen evolutions of more than 91% yield. And I can summarize these things in healthcare. I have used that antibacterial and anti-cancer peptides. We can use these peptide-based materials for 3D and 2D cell cultures and drug delivery. In environmental remediations, we can use these things for removing toxic organic dyes and toxic metallons. And metallogels have been used for using water splitting. And you see, I want to say a few words about this. So far, we have just done this more animal experiment and other things. We didn't check the immunogenicity and mutagenicity of the peptides to get real delivery vehicles. And we are also in search of new reusable biomaterials to clean up this wastewater. Between the imagination and reality falls the shadow. That means there's a huge gap between a cup and a lip. If you think of many of the problems, only few of them will materialize, and they will just give you some name frame recognitions and some papers. This is my recent group, all collaborators whose name has been listed here. Sorry, I unknowingly missed that ANRF, this for financial support, and thank you for your kind attention.
Yeah, let us thank Professor Arindam Banerjee for his very interesting presentation.
Oh, sure.
Sir, a quick clarification. You showed ovarian cancer. Was it done in vivo or in vitro? Did you
that is not in vivo. In vivo study, we have started with a collaborative work. These are all in vitro.
In vitro? Okay, so cell line you used.
Cell line we have used. That SKVO3. That's in also collaborations with one of the lady scientists from CNCI.
That makes me ask another question.
Sure.
How do you know that cell line has not lost its specificity? Because cells live when they are in culture, they tend to lose their specificity. So first thing is to ensure that what is that control is the question. Telling I respect that. It's a lot of work which you have shown, and I respect that. But despite all those, the tricky question is, how do you ensure that this particular cell line has not lost its specificity? This is the question.
Right now I cannot tell because we have done several cell lines, control healthy cell lines from the same organ and from different organ also, and checked our this cell viability assay. And here this one of these peptides, that triphenyl phosphine containing peptides, which targets its mitochondria, is active in the around 180 to 200 nanomolar concentrations, and that is the peptides, not the aggregates. But when they just exhibit that antibacterial things, that concentration is much higher. That's submicromolar things.
So this cell line, was it affected? Do you know?
Offhand, I cannot say.
Because, if you're talking about these kinds of cancers, oftentimes you do find human papillomavirus infection. Cervical cancer most, but sometimes with ovarian cancer as well. So that needs particular
thank you for your
pathogen
suggestions.
can change your...
Yeah, I know.
Thank
Yeah,
you. Thank you.
He's having the questions, yeah.
So, are there proper structure-activity relationships in terms of which molecules can be encapsulated by which hydrogel? And can they encapsulate large molecules like proteins?
In principle, yes, but still it's at the age of infancy. This is because the major problem is to design some good hydrogelators. The fine-tuning of hydrophobicity and hydrophilicity, correct? Now, after making these peptide-based hydrogels, we are looking for some amphiphilic molecules to just bind, because that's a physical absorption, not the chemical absorptions, correct? And see, if it's for micelles, our binding is correct, and if it's a hydrophobic, it can go to the core of these things, micelles. But another problem with the micelles, they're having, like organic chemistry, vulvalines. It's a very fluctuating structures. They're not very homogeneous. We did this GLS and other physical studies. They're, I try to say, much homogeneous. Even for the fuse structures, tame, they are just inner, total diameter, inner plus outer, vary from maybe 15 to 35, sometimes 45 nanometers.
Which have antibacterial or anti-cancer property, they work in micromolar concentration.
Exactly.
Did you find that will be, just let me complete, that will be having a higher probability of its practical use in clinical practice, number one. Number two, most of these peptides are positively charged.
Exactly.
And they have low solubility issue. Is that correct?
No, not very low solubility.
Yeah.
Because if it's solulase, they only form these soluble aggregates, neither too soluble nor too insoluble. Right. Their solubility is just in between, because they're amphiphilic molecules. They're having this positive head group and that lipophilic things at the tail type of things. And in between, CONA secondary amide bonds. They are also having some polarity.
Because we are hearing about this peptide story as a antimicrobial or anti-cancer for a long time.
Why this
but why they have not come into clinical practice?
Their use are limited. This is because most of the cases people are using alpha-L amino acids. So you cannot do this internal injection and all these things. Their proteolytic stability and enzymatic stability is very less. What we are making, we are purposefully using D-amino acids, beta-alanine and some of the other things to down that concentrations to just make some real deliverable molecules which can give
maybe you can discuss more.
Thank you.
So let us thank again Professor Arindam for a very interesting presentation.